Hello students, we are dealing with mechanical properties of the fluid, in which we have seen the definition of pressure. Pressure is given by force per unit area, perpendicular force acted on unit area. The pressure is measured in SI unit as a Newton per meter square or Pascal. Okay. Then we have calculated pressure exerted by liquid column. That pressure is given by H rho g, where H is the height, density and acceleration due to gravity. This equation we have derived in last session. Now we are going to see atmospheric pressure. So what is atmosphere? If we consider Earth, then the matter surrounding to Earth is said to be atmosphere. Okay? This atmosphere has certain mass, so it exerts a thrust. This atmosphere exerts a thrust or a perpendicular force on the Earth's surface. So this perpendicular force per unit area is nothing but the atmospheric pressure. Clear? What is atmospheric pressure? The pressure exerted by, or you can say the perpendicular force, the thrust exerted by atmosphere on the Earth's surface. Okay? This is atmospheric pressure. At the Earth's surface, and exactly on the Earth's surface, if we measure atmospheric pressure, then it has magnitude. Atmospheric pressure denoted by P0. It has magnitude 101325 Pascal. Okay, this is the atmospheric pressure at Earth's surface, and it is also observed that the atmospheric pressure has largest value at the Earth's surface. As we go at higher altitude from the Earth's surface, then atmospheric pressure decreases. What? As we go higher altitude from the Earth's surface, then the magnitude of atmospheric pressure is decreases. Atmospheric pressure has highest magnitude, largest magnitude at exactly Earth's surface. Okay. Similar to pressure, density at Earth's surface, density is also higher. Density of the atmosphere at the Earth's surface is also largest, and density decreases with increasing altitude. Okay. This is the concept of atmospheric pressure. Now, next is expression for pressure inside the liquid. Let's consider a container. This container consists of a liquid. Now let an imaginary cylinder inside the container, inside this container. Okay. This container having cross-sectional area capital A. We have taken a container containing a liquid of density rho. Let an imaginary cylinder into container of cross-sectional area capital A. Okay. Now there is a liquid surrounding the imaginary cylinder. Let's consider 2 points, top point and bottom point of that imaginary cylinder. There is a liquid above the top, also there is liquid below the top of that container. Now let's take two reference points, x1 and x2. First reference point x1 at the top position of imaginary cylinder, and second reference point x2 at the bottom of the imaginary cylinder. And both the references, both the points are taken from bottom of the container. First, this top of the container is at distance x1 from bottom of the container, and this bottom of the imaginary cylinder is at distance x2 from the bottom of the container. And distance between these 2 points, that is h is the height of that container. Let x1 minus x2 is equal to h, v height of imaginary cylinder. Where x1 and x2 are distances taken from bottom of container. Okay. Now top and bottom of imaginary cylinder, which consists of, there is a liquid above and below. So due to before that, let's calculate mass of imaginary cylinder. Mass of imaginary cylinder is given by mass is equal to density into volume of that cylinder. So density we have taken here as rho, and volume of that imaginary cylinder can be taken as x1 minus x2 into, okay, what is volume of container? Volume of cylinder, x1 minus x2 is the height into cross sectional area. Height into cross sectional area, that is nothing but volume of imaginary cylinder. So mass of imaginary cylinder is rho into x1 minus x2 into A, cross sectional area. Now let's take forces acted on the imaginary cylinder. Forces acted on imaginary cylinder. First forces. There is certain liquid, specific amount of liquid above the top surface of the imaginary cylinder. So due to that liquid, the force acted along downward direction. Suppose that force is F1 bar. Okay, F1 bar is the force acted by liquid above the top of cylinder. First force we have taken F1 bar be the force acted by liquid above the top of cylinder, and this is downward force. This force is along downward direction, vertically downward. Also, second force, there is specific amount of liquid below the imaginary cylinder. So this liquid also exerts a upward direction force. Upward direction force at the F2 bar. F2 bar, the force acted by liquid below the cylinder, and this force is along upward direction. Okay, these two forces acted. Also, we can take the another force acted, that is nothing but gravitational force, and we know gravitational force is always vertically downward direction. Third is gravitational force. It is also vertically downward direction. Okay, these three forces acted on the imaginary cylinder. F1 bar, which is along downward direction, F2 bar. Instead of F3, let's write mg here, gravitational force. F1 bar, which is vertically downward, F2 bar vertically upward, and third gravitational force, which is also vertically downward direction. Okay, now if we consider a equilibrium condition, then we can add these forces, and if we add these forces, then we get F2 is equal to F1 plus mg. Get it? This is the equation of forces. Now we can take the pressure here instead of force. As this F1 force acted perpendicularly, so we can take pressure at top as a P1. Due to this force, pressure P1 acted, force per unit area. Due to this force F2, the pressure P2 acted, that is also force per unit area. Now, but F1 is equal to P1 into A, and F2 is equal to P2 into A. For both the forces, we have taken same cross-sectional area because of height of that cylinder is very small. We can substitute both the values into our equation so that we get P1A is equal to P2A plus mg. Let's substitute value of m from equation 1. You will get P1A is equal to P2A plus what is m? Rho into x1 minus x2 into a, and acceleration due to gravity remains as it is. Area of cross section of the cylinder can be cancelled here. So we get equation P1 here the pressure is P2 and here the pressure is P1. Here F2 is P2E. Okay, LHS is our P2E. So after cancelling cross section area, we get P2 is equal to P1 plus rho x1 minus x2 into g. Okay, we get the equation P2 is equal to P1 plus rho into x1 minus x2 into g, acceleration due to gravity. And this expression is for pressure inside the liquid. Clear? This is the pressure inside the liquid. Okay, after calculating this equation, now we are going to calculate expression for pressure below the liquid surface. Here, in this equation we have calculated pressure inside the liquid. This imaginary cylinder was inside the liquid and we have calculated at the top surface of the cylinder and at the bottom surface of the cylinder, P2 and P1. Okay. Now we have to consider this cylinder is at the top surface, at the top of free surface. This container consists of a liquid in which we are taking a imaginary cylinder, but top of the imaginary cylinder is coincide with the free surface. Free surface means the surface of liquid is in contact with air, that is free surface of liquid. We have taken imaginary cylinder, or top of the imaginary cylinder is exactly coincide with the free surface of liquid. That is our point x1. Our point x1 is at free surface and point x2 is below the depth h. Okay, then consider imaginary cylinder in such a way that top of cylinder is coincide with free surface. Okay. Now, as our point x1 is at the free surface, so the pressure exerted at the top surface is nothing but the atmospheric pressure. Okay. Hence, P1 is equal to P0, that is atmospheric pressure. Okay. Our pressure P1 was here, but here in this case that point is inside the liquid, but now in this case that point is at the free surface of liquid. So the pressure exerted at that point is due to the atmosphere, and that pressure we have taken as atmospheric pressure. Also substitute instead of P2 as a P. Okay. Then instead of x1, let's substitute as 0, because x1, this point we have taken at the free surface. If that point is reference point or at free surface, so we have taken 0, then our x2 will become minus h now. Substitute all these values into this equation, so we get P is equal to, instead of P2, P is equal to, instead of P1, atmospheric pressure P0 plus rho remains as it is, rho is density, x1 as a 0 minus x2 as a minus h, so it becomes plus h, and finally acceleration due to gravitational is as it is, and final equation we get pressure P is equal to P0 plus h rho g. This is expression for pressure below the liquid surface. In this equation, P is called total pressure or absolute pressure. P is absolute pressure, P0 is atmospheric pressure, if P is absolute pressure, P0 is atmospheric pressure, then we can calculate gauge pressure. Gauge pressure, and gauge pressure is the difference between absolute pressure and atmospheric pressure. What is gauge pressure? Gauge pressure is nothing but difference between absolute pressure and atmospheric pressure. Okay, clear? In this equation we got three pressure: absolute pressure, atmospheric pressure, and if we take the difference between these two, then it is nothing but gauge pressure. Okay, we have calculated two expressions for pressures. First, pressure inside the liquid, and the second, pressure below the liquid surface. And now finally we are calculating here pressure above the liquid surface. To calculate pressure above the liquid surface, we have taken the imaginary cylinder is above the free surface of liquid. In second case, top surface of the cylinder is coincide with free surface of liquid, and in last case we are taking bottom of the imaginary cylinder is coincide with liquid surface. Okay, so our pressure P1 at the top of cylinder is taken as P, and the pressure at the bottom of cylinder P2 is nothing but atmospheric pressure. P2 is the pressure taken at the free surface of liquid, and that pressure is due to the atmosphere, due to the air. So that pressure is nothing but atmospheric pressure. Now the distances x1 distance is taken as at distance small d, but this distance is above the free surface of liquid, and x2 is at the free surface of liquid. So we can take x2 as a 0. Let's take x1 as a d, x2 as a 0. Now if we substitute all these values, then finally we get the equation. P is equal to P0 minus d. Instead of height, we are taking d, rho, but density, we are not taking here density of the liquid, because our imaginary cylinder is into the air medium. So we have to take density of air now. Density of air into acceleration due to gravity. This is the expression for pressure above the liquid surface. P is equal to P0 minus d into density of air into acceleration due to gravity. In this way, we have calculated three different pressures. First, pressure inside the liquid. Here. Second, pressure below the liquid surface. Pressure below the liquid free surface of liquid. And third, pressure above the free surface of liquid. Thank you.